example 3. Find one. Determine whether or not f is a conservative vector field. If it is, find a function f such that f is equal to the gradient of f. So again, we're going to use Clairaut's theorem to help. We're going to take the partial of our p, which is 3x minus 2y squared, and we're going to take that with respect to y. When we do that, we get negative 4y. And then we're going to take the partial of our q with respect to x, and we're going to get positive 4y. They're not equal. F is not a conservative vector field. We're done. All right, that's it for that one. We like it when that happens because we don't have to do as much. All right, so let's do the last one. So the last one's kind of putting it all together. We're going to find a function f such that our vector field is equal to the gradient of the function. So we'll have a conservative vector field. And then we're going to use A to evaluate the line integral along the given curve C. Right, so again, if f is a conservative vector field, then the pathway does not matter for our line integral, and that's why the endpoints only matter. All right, and so that's why we can get rid of the integration and just take the endpoints at whatever value that we're in. All right, so A is going to be very similar to, the A part is going to be very similar to example 3. The first thing that we're going to do is we're going to take our partial of y or our partial of x. And so in this case, this is the partial of x. This is the partial function with respect to x. This is our partial function with respect to y. Which one of those looks easier to deal with? Oh, the partial of y. So that's what we're going to start. So that's why I said the partial of y. You know, in example 2, I did the partial of x. In example 1, I did the partial of y. I can choose which one I want to start with. So I take the partial of y, and I want to get back to the potential function, or the original function. And so I take the antiderivative of that. And so when I take the antiderivative of what's on the left, I take it with respect to y, and then I can't forget about, okay, I could have had a gx there, so plus gx. And then I'm going to take the derivative of that with respect to x. When I do that, this is the function that I'm going to get. And I'm going to set that equal to what the conservative vector field had as that part of the function. All right, because that is f of x, xy. Sorry, f sub x of xy. And then I'm going to solve. So, you know, I can cancel out what I can cancel out. What I notice here is that if I distribute the e to the xy, you know, that's going to cancel out with that 1. And it's going to cancel out that e to the xy because of the distribution. So g prime of x is equal to g prime of x. So what I'm told here is, oh, okay, well then g prime of x is equal to 0. Yeah, there should not be a plus g prime of x there. So it should be just g prime of x is equal to 0. So again, we have g of x is equal to k, which we can take k to be 0, so that when we, because again, the pathway is not going to matter, so we're just going to take that k to be 0. And so we get our potential function as f of xy equals x to the x times e to the xy. All right, so now that we have a potential function, now and that potential function based off of our vector field is now going to be a conservative vector field because it's the gradient of f. So now we can go ahead and just take the line integral, and we can take just the net change of the two endpoints. So to find that, again, I'm going from 0 to pi over 2 on t. So I'm going to plug in 0 into r. All right, and again, there's r, there's the x value, there's the y value for r. So I'm just going to go ahead and plug it in for r. I'm going to plug in, I plug in 0, and I'm going to get 1, 0 for the first value, and then when I plug in r pi of 2, I'm going to get 0, 2 for the second value. Plug those in to our function, and we're going to be given 0 minus e to the 0, which is just negative 1. All right? Again, any questions that you have for me, just come back to the original room and I'll answer any questions. But that's it. Again, it's not a very difficult section. And, it's really nice finding